Hello friends, welcome to Quick Learn website, and I am very excited to inform you that in Quick Learn I have recently launched my website, that is www.quick-learn.in. This website is especially for all the engineering and diploma students and those students who will preparing for competitive exams. So in the blog section of the website, you can find the notes of all the electrical and electronic subjects, just like basic electronics, microcontroller, microprocessor, power electronics, and slowly I will add more notes in the website. And if you are preparing for any government competitive exams, then check also my MCQ series, that is multiple choice question series, and previous year question papers. That will help you in your competitive exams. Here I also upload the quiz test or mock test for ONGC, UPPCL, or for different type of competitive exam previous year question papers. Or for latest update, please join my Telegram channel. The link of my Telegram channel I will give in my description box. So stay continue and keep watching and keep visiting my website. Hello friends, welcome to Quick Learn tutorial series. In this video, I will explain you 3-phase inverter with 120-degree conduction mode. This is lecture number 41 of Power Electronics series. So let's start with the topic. Now before I discuss the 3-phase inverter with 120-degree conduction mode, here I give a brief description of 3-phase inverter. 3-phase inverter are basically used to convert DC voltage into 3-phase AC supply. 3-phase inverter are most commonly used in industrial application where we not use single-phase inverter because single-phase inverter are used in domestic applications. Generally, 3-phase inverter are used in high power applications and variable frequency drive applications just like HVDC power transmission. So this is the brief introduction of 3-phase inverter. Now classification of 3-phase inverter. So there are basically two type of 3-phase inverter, 120-degree conduction mode and 180-degree conduction mode. 180-degree conduction mode I have already explained in my previous video. So if you want to study about 180-degree conduction mode, please refer my that video. In this video I will explain you 120-degree conduction mode. But the circuit diagram of both the conduction mode are same. It means the circuit diagram for 180 conduction mode and 120-degree conduction mode are same. So this is the circuit diagram of 3-phase inverter. This is common for 120-degree and 180-degree conduction mode. Here we use 6 thyristor and 6 diode. So 6 thyristor T1, T2, T3, T4, T5 and T6. And we also use 6 diode. Each diode is connected in anti-parallel with thyristor. So D1 diode is connected in anti-parallel with T1 thyristor. D2 diode is connected in anti-parallel with T2 thyristor. D3 diode is connected in anti-parallel with T3 thyristor. Same as D4 diode is connected in anti-parallel with T4 thyristor. Same D5 diode is connected in anti-parallel with T5 and D6 is connected in anti-parallel with T6 thyristor. So in this way we connect diode and thyristors. Now this whole circuit is divided into 3 segments. This is the first segment. The first segment consists of thyristor pair T1, T4. This is second segment. Second segment consists of 2 thyristor T3 and T6. This is the third segment. Third segment again consists of 2 thyristor T5 and T2. So in this way we divide the whole circuit into 3 segments. Now the upper thyristor is called positive group thyristor. It means T1, T3 and T5 are called the positive group thyristors. And the lower group thyristor, it means T4, T6 and T2 are called negative group thyristors. So in this way we connect or we divide the whole circuit into segment and positive and negative group. Now come at the load side. Here we use 3-phase star connected load. The impedance of the load is equal. This is the neutral point and the first load is connected from phase A. the second load is connected from phase B and the third load is connected from phase C. So here we see the first segment thyristor is come under the phase A. The second segment thyristor comes under phase B and third segment thyristor comes under phase C. Now come at the source side. We know that the source of the inverter is DC power supply. So here we use battery to provide DC voltage to the inverter circuit, and in parallel with this DC voltage, here we connect a capacitor. This capacitor having high capacitance. This capacitor provide a constant voltage source to the inverter circuit. Now the second function of the capacitor, this capacitor reduce the harmonics fed back to the source. So these two function of capacitor. So this is the whole description of the three-phase inverter circuit. Now we know that in case of three-phase supply, if first phase is started from 0 degree, the second phase is started from 120 degree and the third phase is started from 240 degree. So the phase difference between two phases are 120 degree. Again I will explain you. In case of three-phase circuit, if first phase is started from 0 degree, second phase is started from 120 degree and third phase starts from 240 degree. So the phase difference between two phases are 120 degree. This concept we use later. Now 120 degree conduction. What do you mean by 120 degree conduction mode? How this 120 degree conduction mode is different from 180 degree conduction mode? So in case of 120 degree conduction mode, each SCR conducts for 120 degree. Means the closing time of switches or SCR is reduced to 120 degree instead of 180 degree in 180 degree conduction mode. So this is the basic difference between 120 and 180 degree conduction mode. In case of 180 degree conduction mode, each SCR conducts for 180 degree. But in case of 120 degree conduction mode, each SCR is conduct for 120 degree. So let us assume if one SCR T1 thyristor is start conducting from omega T is equals to 0 degree. So it will conduct for 120 degree. Okay. Now if any thyristor T4 start conducting from 180 degree, so it is also conduct for again 120 degree. It means it conduct from 180 degree to 300 degree. So the conduction of each SCR is equal 120 degree in case of 120 degree conduction mode. So as I have already told, here we see in the circuit diagram, the circuit is divided into three segments. This is first segment, this is second segment and this is third segment. First segment consists of thyristor pair T1 and T4. Second segment consists of thyristor pair T3, T6 and third segment consists of thyristor pair T5 and T2. So this is segment 1, this is segment 2 and this is segment 3. So first we consider segment 1. In segment 1 we have two thyristor T1 and T4. One by one each thyristor will conduct for 120 degree because it is a 120 degree conduction mode. But for every segment simultaneously both the thyristor will never turn on because that will make a short circuit. So first at omega T is equals to 0 degree we provide firing pulse to thyristor T1 and T1 start conduct for 120 degree. T1 conducts from 0 degree to 120 degree. After 120 degree what will happen? We know that half cycle of the sinusoidal wave. This is the full cycle 0 to 360 degree. But half cycle of sinusoidal signal is 0 to 180 degree. Therefore, the remaining 60 degree from 120 degree to 180 degree, neither T1 thyristor will conduct nor T4 thyristor will conduct. At this time interval 120 degree to 180 degree, neither T1 nor T4 thyristor will conduct. Now at omega T is equals to 180 degree, we provide triggering pulse to thyristor T4 and T4 start conducting for 120 degree, that is from 180 degree to 300 degree. After 300 neither T1 thyristor will conduct nor T4 thyristor will conduct. because it is a 120 degree conduction mode. After that, we will again give 2 firing pulse to thyristor T1 and T1 conducts for 120 degree and so on. Now consider segment 2. In case of segment 2, we know that, as I have already told, in case of 3-phase power supply, if one phase starts from 0 degree, second phase is started from 120 degree and third phase starts from 240 degree. So segment 2 is in phase B. So in phase B, we give firing pulse to thyristor T3 at omega T is equals to 120 degree and T3 will start conduct for 120 degree, that is 120 degree to 240 degree. But after 240 degree, here we see neither T3 thyristor will conduct nor T6 thyristor will conduct from 240 to 300 degree. At 300 degree, we again provide triggering pulse to thyristor T6. So T6 conduct for again 120 degree. It means 300 degree to 60 degree. This is the next cycle. This is complete one cycle, 0 to 360 degree, and this is the next cycle. So in this cycle, T6 conduct up to 60 degree. But after 60 degree, from 60 degree to 120 degree, neither T3 will conduct nor T6 will conduct. In this way, we triggered thyristor T6 and T3. Now consider segment 3. Segment 3 is in phase C. So in case of segment 3 or phase C, we give firing pulse to thyristor T5 because we know that if phase A starts from 0 degree, phase B starts from 120 degree, phase C starts from 240 degree. So at omega T is equals to 240 degree, we give firing pulse to thyristor T5. So T5 start conduct from 120 degree, that is 240 to 360 degree, T5 will be conducting. After 360 degree, neither T5 will conduct nor T2 will conduct because it is a 120 degree conduction mode. So for 360 to 60 degree, no thyristor will conduct from segment 3. After at omega T is equals to 360 degree, we give firing pulse to thyristor T2. So thyristor T2 will conduct for 120 degree, that is 60 degree to 180 degree. After 180 degree, 180 to 240 degree, no thyristor will conduct from segment 3, neither T2 nor T5. Now we divide this complete cycle 0 to 360 degree into 6 steps. This is step 1, this is step 2, 3, 4, 5 and 6. Again this is the second cycle. This second cycle is also divided into 6 steps. 1, 2, 3, 4, 5 and 6. First we consider step 1. Here in step 1, between omega T is equals to 0 degree to omega T is equals to 60 degree, 2 thyristor will conduct. Here we see 2 thyristor is conducting, T1 and T6. So here I write in step 1, 2 thyristor is conducting, thyristor T6 and T1. Now in step 2, between 60 degree to 120 degree, again 2 thyristor is conducting. Here we see T1 and T2. Now in step 3, between 120 degree to 180 degree, again 2 thyristor is conducting, T2 and T3. These two. Okay, this one and this one. So T2 and T3. Again in step 4, 2 thyristor is conducting between 180 degree to 240 degree, T3 and T4. Now in step 5, between 240 degree to 300 degree, again 2 thyristor is conducting, T4 and T5. So here T4 and T5. Now in step 6, again 2 thyristor is conducting, T5 and T6. So T5 and T6. So by this we conclude that in each step 2 thyristor is conducting, one from the positive group and one from the negative group, or we can say that one from the upper group or one from the lower group. For example, here we see in step 1, thyristor 6 and 1 is conducting in step 1. Thyristor 1 is from positive group and 6 is from negative group. Again, in step 2, two thyristor is conducting 1 and 2, 1 from positive group and 2 from negative group. Again, in step 3, two thyristor is conducting 2 or 3. So here we see in the diagram 2 or 3. 3 is from positive group, 2 is from negative group. Again, in step 5, 4 or 5 thyristor is conducting. So 4 is from negative group and 5 is from positive group. So we conclude that every step only 2 thyristor is conducting, 1 from positive group or upper group and 1 from the negative group. Now one by one we analyze each step, and first we calculate the phase voltage for each step. Simultaneously we draw the waveform. So here, to calculate the phase voltage, first we draw the simplified circuit diagram of three-phase inverter. In this simplified circuit diagram, here we replace all the thyristor with switches. So this is T1 thyristor, this is T3 thyristor, this is T5 thyristor. As I have already told, these three are the positive group thyristor or upper thyristor. The lower thyristor is T4, T6, T2. These are the negative group thyristor. So all thyristor first we replace with the help of switches. Now these two thyristor T1 and T4 are connected from phase A. These two thyristor T3 and T6 is connected from phase B. Here we see. And these two thyristor T5 and T2 is connected from phase C. Here we see. And this is the neutral point. So these are the positive group and these are the negative group thyristor. Now we calculate phase voltage. So to calculate phase voltage, first we analyze each step and then we calculate the phase voltage VAN, VBN or VCN. Okay. Now first we calculate the phase voltage for step 1. Step 1 is starting from omega t is equals to 0 degree to 60 degree. In this step, two thyristor is conducting T1 and T6. While other remaining thyristor will not conduct. So only two thyristor is behave like a closed switch, T1 and T6. And we know that T1 is connected from phase A and T6 is connected from phase B. So first we draw the simplified circuit diagram. Here T1 is connected, closed switch, and T6 is behave like a closed switch. T1 is a positive group thyristor and T6 is a negative group thyristor. So here we draw the simplified circuit diagram. That is, T1 thyristor is from phase A and T2 thyristor is from phase B. T1 is positive group thyristor, so connect from positive terminal of supply voltage. T2 is from negative group thyristor, so connect from negative terminal of supply voltage. And this is neutral point. Here we see both impedances are equal and connect to the DC input supply. Here impedance are equal, so they share equal voltage. So the voltage across VAN, it means here VAN is equals to the voltage across VNB, because current following in this direction. The direction of current flow is this. So the voltage across VAN is equals to the voltage across VNB. So the VAN voltage is Vs by 2 and the voltage across VNB is Vs by 2. But if we want VBN voltage, that is minus Vs by 2. In this case, VCN voltage is 0. Now after calculating the phase voltage VAN, VBN or VCN, we draw the waveform. So for first step 0 degree to 60 degree, VAN equals to Vs by 2. If this is the Vs by 2 magnitude, we draw the waveform. VBN is minus Vs by 2. So if this is 0, this is minus Vs by 2. So we draw the waveform. Now VCN equals to 0. So for step 1, VCN equals to 0. So this is the waveform for step 1. Now here we calculate the phase voltage for step 2. Step 2 is between 60 degree to 120 degree. Here two thyristor is conducting T1 or T2. So here we see in the circuit diagram, T1 is positive group thyristor and connected from phase A. T2 is negative group thyristor and connected from phase C. Now we draw the simplified circuit diagram. We know that T1 is connected from phase A and it is a positive group thyristor. So phase A is connected from positive terminal of supply voltage. So here we see in the circuit diagram, phase A is connected from positive terminal of supply. Now T2 thyristor is negative group thyristor and connected from phase C. So phase C is connected from negative terminal of supply voltage. So here phase C is connected from negative terminal of supply voltage. So in this way we got the simplified circuit diagram. This is neutral point and here we see both the impedances of load is same, that is Z. So if current following in this direction, because we know that current always flow from positive terminal to negative terminal. So upper terminal is positive and lower terminal is negative. So current flow from in this direction from A towards C. So the voltage across the load is, here the voltage is, total voltage is Vs. Vs voltage is divided into two parts, Vs by 2 upper part and Vs by 2 lower part. So the voltage VAN is equals to Vs by 2 and voltage VNC, here VNC is also equals to Vs by 2. So here we see VAN equals to Vs by 2, VNC is equals to Vs by 2. If we want VCN voltage, so that is equals to minus Vs by 2. Okay, this time VBN equals to 0 because here we see in the circuit diagram the phase B thyristor, both the thyristor is turned off this time. Only two thyristor is conducting in phase 2, T1 and T2. Phase A or phase C thyristor. That is why phase B voltage is 0. Now after calculating the phase voltage for step 2, we draw the waveform. VAN equals to Vs by 2. So for step 2, 60 degree to 120 degree, VAN equals to Vs by 2. So here we draw Vs by 2. Now VBN is 0. So this time VBN 0. So here we connect VBN 0. Now VCN minus Vs by 2. So if this is 0, here somewhere minus Vs by 2. So this is the waveform of step 1 and step 2. Similarly, we calculate the phase voltage for step 3. Step 3 is starting from 120 degree to 180 degree. Two thyristor conducting T3 or T2. T3 is from phase B and positive group thyristor. T2 is from phase C and negative group thyristor. So here T2 is from phase C and negative group thyristor. So this is the simplified circuit diagram we get. This is neutral point. Here we see both the impedances are equal if current flow in this direction. So the voltage across VBN is equals to VBN is equals to VNC, that is equals to Vs by 2 or Vs by 2. Because both the impedances are equal, the voltage division is also equal. This time VBN equals to Vs by 2, VNC equals to Vs by 2. If we want to calculate VCN, that is equals to minus Vs by 2 because current flow in this direction. This time VAN equals to 0. So in this way we calculate the phase voltage. Now we draw the waveform for step 3. Step 3 is from 120 degree to 180 degree. It means this step. Here VAN equals to 0 degree. So here we draw 0 degree. Okay. VBN plus Vs by 2. So somewhere here Vs by 2. Here we connect. VCN equals to minus Vs by 2. So if this is minus Vs by 2, we connect here. So in this way we draw the waveform for step 1, 2 and 3. Now we calculate the phase voltage for step 4. Step 4 is between 180 degree to 240 degree. Here two thyristor is conducting this time, T3 and T4. So here we see in the circuit diagram, T3 is the positive group thyristor and connected from phase B, and T4 is the negative group thyristor and connected from phase A. T4 and T3 this time is behave like a closed switch. So phase B is connected from positive terminal of supply voltage and phase A is connected from negative terminal of supply voltage. So from this circuit we got the simplified circuit diagram. This is the simplified circuit diagram. Phase B is connected from positive terminal of supply voltage because T3 is conducting, and phase A is connected from negative terminal of supply voltage because T4 is conducting this time, and this is the neutral point. And here we see both the impedances are equal. If current flow in this direction, so the voltage across load is, total voltage is Vs, and this Vs voltage is divided into two parts, Vs by 2 in the upper part and Vs by 2 in the lower part. So the voltage across VBN, that is VBN, this time is equals to VNA. Both are equal, Vs by 2. So here we see VBN is Vs by 2, VNA is Vs by 2. If we want VAN, so that is minus Vs by 2. This time VCN equals to 0 because here we see phase C thyristor T5 and T2 both are not conducting this time. Now we draw the waveform for step 4. Step 4 is 180 to 240 degree. So this is step 4, 180 to 240 degree. T3 and T4 is conducting. This time VAN equals to minus Vs by 2. So somewhere here minus Vs by 2. Here I draw, see in the waveform. Okay. VBN is equals to Vs by 2. So this is Vs by 2. Now here we draw the waveform. VCN equals to 0 this time. So here we draw the waveform VCN equals to 0. In this way we got the waveform of step 4. Now we calculate phase voltage for step 5 in the same way, 240 to 300 degree. Here two thyristor is conducting, T4 and T5. T4 is negative group thyristor and connected from phase A, and T5 is positive group thyristor and connect from phase C. So here we see phase A is connected from the negative terminal of supply voltage and phase C is connected from positive terminal of supply voltage via T5 thyristor because both are work like a closed switch. So here we got the simplified circuit diagram. Phase C is connected from positive terminal of supply voltage. Phase A is connected from negative terminal of supply voltage. Now if current flow in this direction, because current always flow from positive terminal toward negative terminal. So the direction of current is this. So the total voltage across the load is also equals to Vs. Okay, but this Vs voltage is divided into two parts because neutral point is there. So VCN voltage is Vs by 2 and VNA voltage is also equals to Vs by 2 because both the impedances are equal. So here this time VCN equals to Vs by 2, VNA is equals to Vs by 2. But if we want VAN, that is equals to minus Vs by 2. This time VBN equals to 0 because here we see phase B thyristor T3 and T6 is not conducting in step 5th. Now we draw the waveform for step 5th, 240 to 300 degree. 240 to 300 degree. Here thyristor 4 and 5 is working. VAN is equals to minus Vs by 2. So here we draw the minus Vs by 2 waveform. VBN equals to 0. So VBN we draw here 0. VCN equals to plus Vs by 2. So here somewhere this is plus Vs by 2. So this is the waveform for step 5. Now similarly for step 6 we also calculate the phase voltage. Step 6 is varies from 300 degree to 360 degree. Here two thyristor is working, T5 and T6. Here T5 is the positive group thyristor and connected from phase C, and T6 is negative group thyristor and connect from phase B. So this time phase B is connected from the negative terminal of supply voltage and phase C is connected from positive terminal of supply voltage via thyristor T5. So here we get the simplified circuit diagram. Phase C is connected from positive terminal of supply voltage. Phase B is connected from negative terminal of supply voltage. This is the neutral point. Both the impedances are equal. So the voltage across VCN is equals to VNB, that is equals to Vs by 2. Okay. So VCN is equals to Vs by 2. VNB is equals to Vs by 2. If we want to calculate VBN, VBN is equals to minus Vs by 2, and this time VAN is equals to 0 because phase A thyristor is not working this time. Now we draw the waveform for step 6. Step 6 is from 300 to 360 degree. Here VAN equals to 0. So here we draw 0. VBN is equals to minus Vs by 2 and VCN is equals to Vs by 2. So in this way we draw the waveform for one complete cycle 0 degree to 360 degree. Similarly, you calculate the phase voltage and draw the waveform for further step or the second cycle. Now we have to calculate the line voltage. What do you mean by line voltage? First consider if this is point A and this is point B. If the voltage across point A is VA and the voltage across point B is VB. So the potential difference between these 2 points is called line voltage. That is called VA minus VB. So here to calculate line voltage, because it is a 3-phase circuit, we have to calculate 3 line voltage VAB, VBC or VCA, because it is a 3-phase circuit. VAB calculated with the help of this formula VAN minus VBN. VBC calculated with the help of this formula VBN minus VCN, and VCA calculate from this formula VCN minus VAN. And these VAN, VBN and VCN are the phase voltage. So we can say that we calculate line voltage with the help of phase voltage. So here again step by step we analyze the phase voltages and we calculate the line voltage. So first we calculate the line voltage VAB. To calculate line voltage, here we use the phase voltage waveform. With the help of this phase voltage, we calculate the line voltages. Okay. So for step 1, 0 to 60 degree, see right hand side in calculation, VAB equals to VAN minus VBN. So what is the value of VAN? See in the waveform, VAN equals to Vs by 2 in step 1 and VBN equals to minus Vs by 2. So here put in the calculation, VAN equals to Vs by 2. So Vs by 2 minus Vs by 2. Minus plus. Okay. 2 or 2 Vs. So 2 cancel. We get Vs. So for step 1 VAB equals to Vs. Same for step 2. VAB equals to VAN minus VBN. VAN equals to, see in the waveform for step 2, VAN Vs by 2. Okay. VBN 0 this time. In step 2 VBN 0. So both the value put in the calculation here. Right hand side VAN Vs by 2, VBN 0. Both equals to Vs by 2. Okay. Same for step 3. VAN minus VBN. For step 3, here we see in the waveform, VAN is 0. VBN Vs by 2. So VAN 0 and VBN Vs by 2. So we get minus Vs by 2. Okay. For step 4, VAN minus VBN. So VAN for step 4. For VAN is minus Vs by 2. So write here minus Vs by 2 minus VBN plus Vs by 2. So put here Vs by 2. So these after calculating we get minus Vs. For step 5, VAB equals to again VAN minus VBN. VAN value for step 5 minus Vs by 2. Okay. And VBN is 0. Here in the calculation VAN is equals to minus Vs by 2. VBN 0, we got minus Vs by 2. Same for step 6. So in this way we calculate the line voltage VAB. Now we draw the waveform. So for VAB line voltage, we have to draw the waveform. So this is VAB. For step 1, see from the calculation side, VAB equals to Vs. So here we draw in the waveform, this is Vs. Okay. For step 2, the value of VAB is Vs by 2. So if this is Vs, see in the waveform, this somewhere here Vs by 2. Okay. Now we join. Now at the right hand side, step 3 value is minus Vs by 2. So draw in waveform. Here minus Vs by 2. Okay. Again for step 4, value is minus Vs. So if this is minus Vs by 2, so here somewhere minus Vs. So here we draw. Again for step 5, here see in the calculation, the value is minus Vs by 2. So this is minus Vs by 2. So here we draw minus Vs by 2. Again for step 6, same calculation we done. We got Vs by 2. So here we draw. So in this way we calculate the line voltage VAB. Similarly, you calculate line voltage for VBC and VCA with the help of phase voltage. So this is the whole calculation of 3-phase 120-degree conduction mode. Hope you like the video. If you have any doubt, please comment in the comment box. And please like, subscribe and share my channel with your friends and juniors. If you want the notes, please visit my website, that is www.quick-learn.in.